We present CBR-foX, a novel generic posthoc case-based reasoning method for the explanation of time series forecasting. Some important points about this method are the following. That includes a mechanism to generate cases from the time series. These cases are based on windows and the length of windows is completely modifiable. And a CBR recovery algorithm along with a novel similarity metric which allows to detect which cases are most like the target. Several CBR adaptation strategies, an automatic evaluation for the most like cases, and this method is ready to use and generic for any time series forecasting model. Now, this XCBR method is headed for domain experts who doesn't have technical skills in programming to understand the output of this one, and therefore the method can be useful to government authorities to prevent natural disasters such as hurricanes. The explanation strategy, as can be seen in the slide, consists of generating windows from the time series. These windows are analyzed by their components and their next element is compared to the next element of the target respectively. In other way, these are the steps for this explanation method. As it was mentioned, the first step is the case-based generation. The second is the novel similarity metric combining shape and magnitude to evaluate the windows. The third step is the retrieval strategy to avoid local nearest neighbors duplicates using noise mitigation technique. This is so important due to allow retrieve only the true neighbors which are the most likely to target and no others which can be noise and therefore it causes a bad result for the explanation. And the last step is the generic visualization method to explain results to users through explanation by example. This is the graphic implementation that allows the user seeing all the data and best windows which explain the prediction. This generic visualization allows the user to configure the number of nearest neighbors displayed. The user can apply for all the best results or for a few ones. Besides, the method can recreate a new case base that is the average of all the most similar windows based on the minimum, maximum, or median of each window. So this generic implementation allows many ways to visually analyze the method results. As it is shown in the slide, the case-based generation scrolls through the time series and while it creates windows which are the case-based, all windows conserve the components data for later analysis. Now, part of the core of this method is the novel similarity metric. Along with this metric, it's possible to create a correlation among the data and be compared to the target. This is the part more important for being able to detect the nearest neighbors. This metric uses the Pearson's correlation and the Euclidean distance. The formula represents the combination of these metrics to create a new one, which is capable to evaluate how the data of each window created is so similar in accuracy and if there is a pattern and how far the window from the target is. In this part, the first image with all that noise is the result of applying the formula to the time series and after to standardize all the data. Now the current step is to find the nearest neighbors, but due to all that noise it's so complicated to retrieve the real ones because are many neighbors so close to each other, and a filter it must be applied to the time series to remove the noise, and in that way it will be more efficient. So as it's shown, for applying the filter, the time series get a cleaner shape and getting the nearest and worst neighbors is very easy. As it was mentioned before, this includes a generalization visualization method which allows to see the best cases similar to the target. In this slide, we can observe the way the window is presented and this visualization can show the components of the window. The point marked in the right side of each graphic represents the following day and it compares to the following day from the target window. To assess the similarity of the prediction to the next nearest neighbor days, we use the mean absolute error formula, which calculates the average distance between the prediction and the window in each component. So, making a summary of this method, we can mention 6 features, which these features are the post hoc explanation system, the way to get the time window case based on the size method, the combined correlation index, which is a new metric to deal with both morphological similarity and absolute proximity when the windows are compared to the target window, the evaluation method for the explanation quality, and notice that the method doesn't need who anyone got technical skills about machine learning to use it, and the last one, this method is ready to be reused with any model. And this is the CBR-foX method, a generic post-hoc explanation method which is totally independent of the forecasting model and ready to use source code. Thank you for watching.